Hello my friends and welcome back to the Today Machine channel. This is the process in which the main raw material, scrap iron, is melted in an electric furnace, refined, and cast to produce slabs, steel pieces, which are semi-finished products. The journey begins with the careful selection and inspection of scrap iron. Different types of scrap iron are processed depending on the final product requirements. The raw materials, once mixed according to specific recipes, are placed in large baskets and transported to a 200-ton electric furnace, one of the largest of its kind in Japan. The melting process is centrally controlled, utilizing a high-energy arc and oxygen to rapidly melt the materials. The electrodes that generate the arc are held by arms made from aluminum alloys, chosen for their excellent conductivity and strength. The smelting process occurs at an intense temperature of 1,600 degrees Celsius. During this stage, a technique known as the transformation exposure method is used to facilitate slag separation, which helps reduce impurities in the molten metal. Following smelting, the molten steel is transferred to the Toribe refining furnace. Here, further impurities are removed, and the chemical composition is finely tuned by adding essential elements. The composition is monitored using an emission spectrometer to ensure precision. A rice-picking turret is used to exchange the toribe, allowing for seamless continuous casting without interruptions. The molten steel is then fed into a mold through an isolation tube, where it undergoes cooling by the mold's up and down vibration. This controlled process ensures the formation of uniform, semi-finished slabs. Advanced technologies, including electromagnetic stirring devices and management deterioration devices, are employed to enhance the internal quality of the slabs. Finally, the slabs are cut to specified dimensions and are immediately transferred to the rolling process. By minimizing temperature loss during this transition, energy efficiency is maximized, and Scuba steel plate can achieve a highly efficient operation by directly connecting the refining and rolling processes. The hydraulic radial forging machines of the SMX type from SMS Mir represent a significant advancement in precision forging technology, offering high performance and flexibility. These machines are globally recognized, with over 10 units sold across various continents in the past decade. The SMX 818 meganewtons model, for example, at the Czech Republic's Vitkovice hammering facility, is an exemplary machine featuring a press force of 18 meganewtons, a tool opening of 800 millimeters, and the ability to handle ingots up to 8 tons. Once the ingot is removed from the furnace, the process is fully automated. The ingot is positioned with precision in the loading manipulator, and the forging process begins, guided by the technology software, ComForge. This software calculates the pass schedule, ensuring optimal forging parameters for over 400 stored materials with flow curves in its database. The initial passes ensure solid forging up to the material core, confirmed by telegraphic examinations that demonstrate a homogeneous microstructure throughout the radius. During forging, the manipulators operate under computer control, ensuring synchronized movement. The carriage advances at a steady pace, with the tong unit stopping in sync with the forging strokes. This synchronization between manipulators enables a seamless transfer of the workpiece, ensuring precise forging results. For example, the SMX can produce complex forms like a double railway axle directly from the ingot in one heat, which is a significant economic advantage over traditional open die forging. The SMX-type machines are versatile, capable of forging round, square, and octagonal long products, as well as flat products with varying edge profiles. They can even forge thick-walled seamless tubes with minimal wall thicknesses over a mandrel. The innovative press cylinders allow for up to 240 strokes per minute, depending on the machine size, ensuring high productivity, precision, and surface quality. The near-net shape production minimizes the need for extensive machining, resulting in high-quality, energy-efficient workpieces with a high material yield. The production process of crane hook block begins with the selection and cutting of raw materials to the required size. Precision cutting is essential to ensure that the subsequent processes can be carried out efficiently and that the final product meets the necessary specifications. In this stage, the cut material undergoes upsetting or drawing out processes where it is compressed or elongated. Upsetting increases the diameter of the material at a specific section, enhancing its strength. The steel is then heated to a specific temperature, making it more malleable and easier to work with. This heating is usually done in a furnace, where precise temperature control is crucial to avoid overheating or underheating, both of which could affect the material's properties. Once heated, the steel is bent into the general shape of a crane hook. This bending is often done using hydraulic presses or other bending machines, ensuring that the material maintains uniformity in thickness and curvature. The bent material is then placed into a forging machine where it is hammered or pressed into the final shape of the hook block. Forging under high pressure improves the grain structure of the steel, significantly enhancing its strength and durability. After forming, excess material is trimmed off to achieve the desired dimensions and shape. This step ensures that the hook block adheres to precise specifications and eliminates any unnecessary weight that could impact its performance. The hook block then undergoes heat treatment, where it is heated and then rapidly cooled in a controlled environment. This process, known as quenching and tempering, increases the hardness and toughness of the steel, making it more resistant to wear and fatigue. Finally, the hook block is machined to refine its dimensions and surface finish. Machining involves turning, milling, drilling, and grinding to achieve the exact tolerances required for the hook block to function safely and effectively in crane operations. Fabricating a forged crane hook involves a series of precise and carefully controlled processes, each critical for ensuring the hook's strength, durability, and safety in lifting applications. The process begins with forging, where a billet of high-strength steel is heated to a malleable temperature and then shaped into the desired hook form using powerful hydraulic presses or hammering techniques. This step imparts the essential mechanical properties to the hook, including toughness and resistance to fatigue. Once forged, the hook undergoes heat treatment to further enhance its mechanical characteristics. This process typically involves heating the hook to a specific temperature, followed by controlled cooling, either by quenching in oil or air, and then tempering to reduce brittleness while maintaining hardness. Heat treatment ensures the crane hook can withstand heavy loads without deforming or breaking. After heat treatment, the hook is trimmed to remove any excess material or flash resulting from the forging process. This is done using precision trimming dies to achieve the exact final dimensions and shape required for the hook's application. The next step is sandblasting, where the hook surface is cleaned to remove scale, rust, and other impurities. This step not only improves the hook's appearance but also prepares it for any subsequent surface treatments or inspections. Finally, the hook undergoes grinding to smooth out any rough edges, ensuring a uniform surface finish. This step is crucial for eliminating stress concentrators that could lead to cracks or failures during operation, ensuring the forged crane hook is safe and ready for use in demanding environments. This is known as the rolling process, which is a crucial step in transforming the slabs into high-quality steel plates. The process begins with slabs, produced in the steelmaking stage, being directly sent to the reheating furnace. Before entering the furnace, the slabs are trimmed to the required dimensions. The furnace heats the slabs to temperatures exceeding 800 degrees Celsius using highly efficient, low nitrogen oxide (NOx) burners, designed to minimize energy consumption and environmental impact. Once the slabs reach the desired temperature, they are extracted from the furnace. Any scale, an oxide layer formed on the surface during heating, is removed using high-pressure water sprays. The clean slabs are then passed through a 4-high rolling mill. Here, they are rolled to specific thicknesses, widths, and lengths according to customer requirements. The rolling mill is equipped with advanced technologies, including automatic gauge control, AGC, automatic width control, AWC, and hydraulic systems that ensure precise control over the dimensions. Additionally, gamma-ray thickness gauges and high-capacity process computers further enhance the accuracy and quality of the rolled steel plates. The rolling line's operations are monitored and controlled from a central control room, ensuring smooth and efficient production. After rolling, the plates are cooled using a cooling device and then flattened in a hot leveling machine, which ensures the plates have a uniform, flat surface. In the inspection line, the plates undergo quality checks and their surfaces are marked for traceability. Depending on customer specifications, additional markings or embossing can be applied. Finally, a 2,000-ton press and a cold leveling machine finish the plates to the required flatness, ensuring they meet the highest standards before being shipped to customers. Worthington Cylinders utilizes a high-grade chromoly alloy, selected for its excellent properties, such as grain structure, impurity levels, and micro-cleanliness. These properties are critical in ensuring the strength and durability of the finished Scuba cylinders. The raw material undergoes a process of spheroidizing and annealing to enhance ductility, which is vital for the deep draw operations that follow. The deep draw process begins with the first draw or cupping press, applying up to 800 tons of force to shape the material into a cup. After each draw, the cup is stripped from the mandrel using stripper jaws. The cups are then subjected to annealing, cleaning, and re-lubrication before undergoing additional draws. The final draw, often requiring up to 250 tons of force, refines the cylinder's shape. Since draw rates are relatively quick, a flood-type coolant is used to prevent overheating during this stage. Typically, 3 draws are required to produce Scuba cylinders, with each draw reducing the material's diameter and thickness by approximately 60%. This deep draw and ironing process is crucial in achieving the desired wall thickness and buoyancy characteristics essential for Scuba cylinders. After the deep draw process, the open end of the cylinder shell is trimmed to ensure uniformity and length accuracy. The cylinder then undergoes ultrasonic inspection before the hot spinning process begins. In this process, An oxygen fuel gas torch heats the cylinder shell's open end to around 1,600 degrees Fahrenheit. The cylinder is then placed into a spinning lathe, operating at approximately 1,000 RPM, where CNC technology controls the forming of the shoulder and neck areas. The shoulder profiles are typically hemispherical, with a thickness 2 to 3 times greater than the sidewall thickness near the neck. The cylinders are completely closed before heat treatment, minimizing interior oxidation and ensuring a smoother surface finish. The cylinders pass through a direct-fired furnace, followed by an aqueous polymer quenchant, and then a direct-fired tempering furnace. These computer-controlled furnaces ensure optimal and consistent mechanical properties to meet regulatory and customer requirements. Following heat treatment, the cylinders are machined to create the required internal thread and O-ring groove. Synthetic coolants are used in machining to prevent the introduction of hydrocarbons into the cylinders. The cylinders are then shot blasted to remove oxides formed during heat treatment, ensuring excellent surface cleanliness both internally and externally. Testing, marking, and corrosion protection. Before final assembly, each cylinder undergoes hydrostatic testing using the volumetric expansion method. The internal volume and tear weight are recorded, and cylinders are pressurized to the required level based on their specifications. After testing, the cylinders are cleaned with hot water and purified air. The cylinders are permanently marked with essential regulatory information, including specification, service pressure, test date, and serial number. For corrosion protection, Worthington Scuba cylinders receive hot dip galvanizing. The cylinders are submerged in molten zinc and slowly removed to provide a durable and attractive coating. The manufacturing process of hot-rolled bright round bars involves several key steps, starting from the preparation of a polished surface hot-rolled billet. These round bars, with diameters ranging from 8 mm to 50 mm, are typically produced in a 250 rolling mill, which is suitable for small batch orders due to its flexibility, despite certain inefficiencies. Billet preparation and heating. The process begins with a hot-rolled billet, which is polished to ensure a smooth surface. The billet is then heated in a furnace to a high temperature, making it malleable for the rolling process. This step is critical, as the temperature must be carefully controlled to ensure the billet becomes soft enough to be shaped but not overheated, which could cause defects. Rolling process. Once heated, a worker transfers the billet to the rolling mill, where it undergoes multiple passes through rolling slots. These passes progressively reduce the diameter of the billet to achieve the desired size. The rolling process is conducted at high temperatures, allowing the metal to flow easily between the rolls. However, this mill is characterized by low production efficiency, slow rolling speeds, and high labor intensity. The process is time-consuming, with significant gap times between operations, leading to higher energy consumption and production costs. Despite these drawbacks, the 250 rolling mill is advantageous for small batch production. It is particularly well suited for unconventional materials and special orders that are difficult to source or produce in large quantities. Orders as small as 100 kilograms, 500 kilograms, or 1,000 kilograms can be conveniently accommodated, making this method ideal for niche applications where flexibility and customization are required. Post-rolling operations. After the rolling process, the semi-finished product undergoes further refinement. Peeling is performed to remove any surface imperfections and achieve a bright, smooth finish. This is followed by calendering, which improves the surface quality, and straightening to ensure the bars are perfectly aligned. The final product is characterized by a precise outer diameter, OD, tolerance of plus 0.2 millimeters, ensuring that the round bars meet strict dimensional requirements. This is Manan Shahid Forgings Factory, the largest forging house in automotive industry of Pakistan. The company provides high-quality forged, heat-treated, and machined steel components to leading original equipment manufacturers, OEMs, in Pakistan. The forging process begins with the careful selection and testing of raw materials to meet the exact specifications required for each component. The material is sourced in the form of metal billets, which undergo rigorous metallurgical and mechanical tests to ensure quality. Once approved, the billets are sheared to the required size and then heated to high temperatures, typically reaching up to 1250 degrees Celsius, using advanced induction heaters. This heating process makes the metal malleable while retaining its solid state, a critical step for effective forging. The heated billets are then subjected to the forging process, which primarily utilizes closed die forging, also known as impression die forging. In this method, the heated metal is placed between two precision-engineered dies that contain the negative impression of the final component's shape. As the dies close, the metal flows under extreme pressure to fill the cavities of the dies, taking on the exact shape and intricate details of the desired component. This process ensures high precision and consistency in the production of complex parts, making it ideal for automotive and industrial applications. All forging dies are manufactured in-house using state-of-the-art computer-aided design, CAD, and manufacturing, CAM, techniques. These techniques allow for the precise modeling of components in 3D, predicting the behavior of the machining process and ensuring the highest level of accuracy. After forging, the components are subjected to a series of heat treatments, including normalization or isothermal annealing, in modern gas-fired top-hat furnaces with a 1-ton capacity. The accuracy of these furnaces ensures minimal variation in the machining process, resulting in consistent quality. Hardening and tempering are carried out in electric salt bath furnaces, with temperature accuracy maintained within 5 degrees Celsius. To remove scales formed during forging, the components undergo shot blasting, followed by a thorough visual inspection to identify any surface defects. After shot blasting, 100% magnetic particle inspection, MPI, is conducted to ensure that only crack-free components proceed to the next stage. Components requiring machining are then delivered to the machining plant, where all machining jigs and checking fixtures are designed in-house during the development of new products. The plant is equipped to handle a wide range of machining applications, including CNC turning, spline hobbing and rolling, broaching, drilling, grinding, and CNC milling. Frequent checks and the extensive use of inspection gauges and fixtures ensure process controls during machining. Induction hardening of axles up to 1 meter and spindles is also performed at the machining plant. A state-of-the-art CNC coordinate measuring machine is used to check the precision of machined components. Final inspection takes place at the finishing shop, where components are degreased and subjected to a rust prevention process before being packed for dispatch. Parts destined for export are packed with volatile corrosion inhibitor, VCI, paper, either individually or in boxes lined with VCI paper, ensuring their protection during transit. The hot strip mill is designed with cutting-edge technology, boasting an annual production capacity of 4 million metric tons. It can produce a diverse range of products, including multi-phase steels and high-strength pipe grades up to X80. The mill's capabilities include processing slabs into strips with thicknesses ranging from 1.5 to 19 millimeters and widths between 750 to 2,130 millimeters. A key feature of this mill is its slab sizing press, which enables the setting of different finished strip widths from a single slab width. This design allows for high productivity, as the casting machines can operate with just one casting width, optimizing the overall production process. Moreover, the ability to roll slabs during hot charging helps to save energy and increase throughput. The mill includes a 2-high reversing stand, which significantly reduces the slab's thickness. Additionally, the 4-high roughing stand, equipped with a 6-part mill housing, enables the use of compact components, which are easier and faster to procure, thereby reducing lead times. The roughing stand is complemented by a fully automatic width control system that works in tandem with the reversing stand to produce ideal transfer bar geometries. The coil box is another crucial element in the mill's compact design, reducing investment costs and ensuring a homogeneous transfer bar temperature, which contributes to a higher throughput. After descaling, the strip heads and tails are separated by a crank shear before entering the finishing mill. The finishing mill, with an optional 7th stand, is capable of producing high-strength grades. It integrates modern technologies to ensure high product quality, long roll service life, and efficient, environmentally friendly production. Additional advanced features of the mill include a fully automatic roll change system, laminar strip cooling for adjusting material properties, and step-controlled gentle coiling on one of the two coilers. After coiling, the strips are sent to banding machines, weighed, marked, and stored for export or further processing. The container manufacturing process begins with steel decoiling and pre-treatment. This involves uncoiling the steel coil and transforming it into even steel plates. The initial step in this process is shot blasting, where high-speed shot balls and grit are used to remove rust from the steel surface and create surface roughness, which enhances the paint's adhesion. After rust removal, a zinc-rich primer is applied to protect the steel surface. Next, in the parts processing workshop, the steel is processed into various container parts, including side panels, door panels, roof panels, cross members, and corner posts, using cutting, shearing, or bending techniques. The sub-assembly line is where different sections of the container are assembled. The side panel line and roof panel line produce the side and roof panels of the container. The rear frame assembly line is responsible for producing the door panels and the rear frame, while the front frame assembly line produces the front frame. The bottom frame assembly line creates the bottom frame of the container. Once these parts are ready, they move to the general assembly and main welding line. Here, the bottom frame, front and rear frames, and side panels are assembled into the container body. Afterward, the roof plates are installed, completing the container body. Welding is used to seal all gaps in the container body. Following the welding process, the container is subjected to a second round of shot blasting to clean welding smoke, burn paint on welding seams, and ensure a smooth surface. The main welding seams and other critical areas are then pre-coated with zinc-rich primer. After passing the inspection at the OK station, the container enters the painting line, where it is coated with marine-level quality paint. This includes a two-coating system for the interior and a recoating system for the exterior, followed by repetitive drying. Finally, the container moves to the finishing line, where the container floors are installed, decals and customer logos are attached, and container accessories such as locking devices and door gaskets are installed. The container undergoes a watertight test and offline inspection before final field inspection and technical acceptance. The Ramshorn crane hook 25 volts is a robust and reliable lifting component designed for heavy-duty applications. These crane hooks are forged to ensure superior strength and durability, making them ideal for demanding environments. Classified under the 25 volts class, they are specifically engineered to handle substantial loads with ease and efficiency. The material used in the construction of these hooks is a high-grade alloy known for its excellent mechanical properties, including high tensile strength, toughness, and resistance to wear and fatigue. This makes the hooks highly dependable in various industrial settings, especially where safety and performance are paramount. Additionally, the hooks undergo 100% magnetic particle testing, MT, and ultrasonic testing, UT, to ensure they are free from internal and surface defects. These rigorous inspections guarantee that the hooks meet the highest safety and quality standards, providing peace of mind in critical lifting operations.